Hello, my name is Stig Hellebust from the Center for Research into Atmospheric Chemistry. Thank you for the invitation to present at this event. I'm just going to give a little glimpse of some analysis we've been doing on air quality in Cork and Ireland recently. If you have any questions during the talk, please use the app. In terms of expectations, I can say that I was expecting initially that we'd see a reduction in NO2, but maybe not in PM, because with more time spent at home, I would expect a lot more emissions from residential heating, even if there was less emissions from traffic. And of course, ozone has its own story. So we had mixed expectations, but we are going to take the data that we have available from the EPA monitoring network, and we're going to mix that with weather observations from the Med-Air network. And the rationale of that is that when we have a normal situation, emissions are regular and predictable, and they are just modulated by the weather. But if you can normalize the emissions to the weather, then you can make a fairly good stab at predicting the air quality in any given location. So in Cork, we have an atmospheric monitoring station, which has been reporting data to the EPA network since 2017. And we can look back over the years and see, has it changed in 2020? So looking at these 3 months in the last 3 years, you would say, no, it's not really any different during the restrictions this year than it was in previous years. But we're going to take the weather into account, because we know that removal processes depend on the weather. So we have to not just compare the air quality, but we have to compare the weather in the different years. Because the main reason in a given location for variation could be the weather as much as emissions. So we're going to take the historical air quality data with the historical weather data. We're going to merge that into a machine learning model. There are many options here. This talk is not going to be about the model, but just about the outputs of this model. And when we have this model, we can take the weather data and we can put it through the model and just get a prediction, which represents a business as usual scenario. That's what you'd expect to see with normal emissions and normalized to the local weather conditions. In this work, we have taken the same approach that has been reported widely in the UK and Switzerland and other places, which is promoted by David Carslow as Ricardo. And when you have this model, you take your prediction based on the weather data, and you take your measured air quality, which then is the real situation, and you compare that with the business as usual prediction, and you see what comes out. And if you have an agreement, then you would say that, yes, things are normal. If they don't agree, you will say that something has changed, and you're not then blaming the weather. You're not saying the weather isn't what it should be. You're saying that the emissions are not as expected. Something has intervened and biased the model. What we mean by agreement is a different discussion, which we'll skip over. But comparing the predicted and the measured values, then for the 3 years, hourly values is not very easy to look at. So we're going to take the 7-day moving average. And for the first 2 years, 2018, 2019, this was the training period for the model. We have a good fit with an average error of close to 0%. And let's just project that into 2020. And we see a continued good fit, but let us zoom in on that period. And we see how the blue line and the red line overlap for most of the time, sometimes over, sometimes under. We have this period here between the 12th of March and the 18th of May, where we see a difference, especially from the 28th of March. There is a consistent divergence where the red line, the business as usual, is well above the real situation. So there is an overprediction there. So the average deviation from the business as usual is around 3% for the period before and after. But during this period, we have a change from the business as usual of nearly 40%. We're going to look at this in a slightly different way now, because we can sum up the errors. So here we have a positive error, here we have a negative error. If you sum up all the errors, they will be randomly distributed around 0. So you should end up with a cumulative sum of errors that is close to 0, or at least a stable level. And doing that for 2 years, we can see that there is some fluctuation, but it comes back to 0. Keeps coming back to 0. So we have a random distribution of errors. We can project that into 2020, and we still see a fairly level cumulative sum until the 28th of March, when we see a consistent over prediction by the model. So the error keeps adding up until the 18th of May, when things level off again. This means that we're back to a situation where you have over and under prediction in a non-biased way. So we're going to do the same for PM 2.5. And again, we don't see any clear difference. But applying this approach, this model, we can see again a very clear change in the there is a bias from the 28th of March. But what's interesting here is that the PM 2.5 does not come back to normal levels like the NO2. So the model keeps over predicting also after the restrictions were eased. So there is more of a lasting impact, you might say, of the restrictions, or maybe the emissions haven't come back to normal yet, and this would be seen here as well, where you have a period before the restrictions where you have over and under prediction, and then from the 28th of March you might have a consistent over prediction. So we have again 30-40% deviation from business as usual during that period, but it is also more consistent afterwards. In Rathmines we see the same thing. We're not quite back to normal levels yet. In Finglas, however, things are clearly back to normal since the 18th of May. In Ringsend, we are still seeing a more lasting impact. Phoenix Park is well back to normal. We can say a couple of words just about the difference between some sites in Dublin and suburban sites that are more residential, in that in residential sites you will often have much more of an influence on temperature and seasonality, whereas in traffic dominated sites you will see more of an influence purely of the time of day and the wind speed. We looked at a small town in Iscorty, which is usually very dominated by solid fuel burning, and to me it was a surprise that also here you see a big drop in pollution levels, PM, during the period. But here we are also back to normal levels since the May. And we can see we can look at it in temporal trends, and we can work out the differences as for the other ones. But just in summary, these models explain the air quality changes on the basis of just weather and temporal cycles, and that works most of the time because these things are predictable until something unexpected happens, and that's how we could identify the impact of the restrictions, which were quite significant for both NO2 and PM 2.5 levels, but unevenly distributed. And more persistent in some locations than others. But even for both traffic dominated and solid fuel dominated emission environments, we saw this effect. And these models can actually be a useful tool in understanding air pollution. They are computationally inexpensive, which makes them easy to use and pick up and make use of. They do, however, require coordination of meteorological and air quality monitoring. I'd just like to say thank you to Micheál Dwyer and Stephen Somerville of the EPA air quality team. And now we can discuss, take questions. Thank you for listening.